So this week we're going to focus on rigid link buckling. Now, from general theory, though, a system may transition from something that is a stable mode, and the key element here is a stable mode of deformation, to an unstable mode resulting in collapse. So we are about to account for the deformation in equilibrium. So we can calculate deformations using kinematic equations, but we're now going to incorporate those deformations within the accounting for equilibrium in these next 2 weeks. And this occurs in members that have axial compressive forces. So this week, the members are assumed to be rigid. Now, nothing is rigid, but it's going to be modeled as something rigid because the flexibility is going to be in the supporting elements. Next week, the flexibility will be in the column itself and will result in some Euler buckling equations. So we will investigate and take equilibrium in the deformed configuration. So all of our work on free body diagrams, on hinged beams, is about to pay off for us. So the system deforms due to the flexibility of the supporting elements. Of course, that means that we have applied external loads, and those external loads will be in compression. So along these lines, the system has what we would call relatively rigid members. Right? They are more rigid than the members that support them, than the supporting elements. So what we're going to do is use springs to model the stiffness of the supporting elements. Those springs are going to come in two different forms, translational springs and rotational springs. So we are going to apply equations of equilibrium in the displaced configuration. So we're going to do a method called perturbation, or we are going to perturb the system. And so before the material elements yield, right, we may end up with a system that can't hold its current displaced configuration. And we will find out that that does not depend on the size of the displacement. Even something extremely small will become unstable. So here's an example in some determinate structures. So something that is pinned rollered, and say we have a compressive load F in the axial direction. And so maybe perhaps that roller may need to be modeled as something that has some flexibility. It's not infinitely rigid here in the transverse direction. So there's some flexibility involved. So we're going to take equilibrium in a displaced configuration. Here would be another example in something that is determinate with a fixed support. And that fixed support perhaps isn't infinitely rigid but has some rotational flexibility. And we would represent that with a pin and a rotational spring with stiffness K theta. One very common application of this is in soil structure interaction. And soil has flexibility to it. In comparison to a structure, the soil would be modeled with translational and rotational springs, especially when doing dynamic analysis of soil structure interaction. Springs are often used in soil structure interaction when analyzing a building for dynamic, either earthquake, most likely earthquake loading, to understand how the soil and the structure interact. The soil stiffness will be modeled with a series of translational springs and rotational springs, as the ground is not infinitely rigid when we put a building on it. We'll spend a few moments deriving some of these spring constants K. So we're about to see several structures that we are going to model with rigid links with springs attached to them. So here's how we would end up with spring constants derived. So if we have an axial rod of length L with an external applied load F on it, and so we're going to go back to the kinematic expression. So on the left-hand side, we've got U B, the axial movement of point B minus the axial movement of point A, right? That is the stretch across element AB. Integrating the right-hand side for this element, we've got an internal force which would be equal to the applied external load. So that's a constant that would come outside of the integral. So there's F over AE, and we're just going to integrate over the length of the element, the unity function. That just ends up with the length of the element. So we end up with the stretch of the element is going to be the force times the length over AE. Using a spring analogy between points A and B, we can use a translational spring. The force in that spring would be the stiffness times the stretch of the spring. Right? The force, there won't be a force in the spring unless we have relative movement between A and B. So that term, right, that is a stretch term. Those are two movements compared to each other. So if those are different, we've got a stretch. And so the stretch would be equal to the movement of B minus the movement of A. So the stiffness of that spring would be equal to the force in the spring divided by the stretch of the spring. So if we just shuffle that around a little bit, force is equal to a stiffness times the stretch, and that stiffness becomes AE over L. So just checking the units on that. Units of area are length squared. Units of E would be force over length squared, divided, whole thing divided by a length. Length squared cancels, so we end up with units of stiffness. So this AE over L would work to model an axial rod. Take a look at a torsional rod. So we've got a rod fixed at one end and applied torque T at the other. And so JG over some length L, we'll say that J and G are constant. So going back to the kinematic expression, we've got the angle of twist at B minus the angle of twist at A. That would be the relative angle of twist is equal to the integral of T over JG, again where T is the internal torque. So the angle of twist between those 2 points is going to be T times the length of segment AB over JG. Again, that only works if between A and B the torque, internal torque, is a constant. So the spring analogy would be a rotational spring, and that rotational spring would provide a restoring moment, and that moment would be equal to the spring constant times the stretch. But for a rotational spring, the stretch is a rotation. So the moment is equal to k theta times the angle of twist between those 2 points. So the spring constant is going to have different units, and it's going to be the value of moment divided by the angle of twist. So just a little bit of a new concept there with a rotational spring, but we'll look at that angle of twist between A and B. We'll call that theta. Over here we would have our constants TL over JG. Shuffling that around, torque divided by angle of twist is equal to JG over L. That's going to be the spring constant. So you can think of it here as the moment, or the torque T, is equal to K sub theta times theta. So K theta is equal to JG over L. Let's do a quick dimensional analysis. Units of J are going to be length to the fourth, the polar moment. G has units of force over length squared divided by length. So we end up with units of moment, or force times length. It would be the units of the rotational spring constant. So taking a look at some beams. Now beams would have both rotational and translational stiffness. And so from a translational point of view, let's take a look at a cantilever beam with a point load out at the end. So that can actually be modeled as a spring. And how we're going to calculate that spring constant, we're going to take the load P divided by the deflection out at the end of the beam. So however far that load P causes deflection, we'll be able to model that as a simple spring. So this just comes from a table lookup, looking in the flexural table. And so the deflection at the free end of a simple cantilever with a point load, PL cubed over 3EI. Invert, we'd end up with 3EI, P's will cancel, over L cubed. So that would give us the value of the translational spring if we wanted to model the beam and that point load as a simple spring. Take a look at a couple other beams here. So we've got a simply supported beam with a load P right in the middle at L over 2, so the spring constant, right? Keeping in mind how would we be able, could we model, again, just at the location of the applied load, could we model that with a simple translational spring? We could. We'd have the load P divided by the displacement at the location of the applied load. So working this out, we would use the flexural table, and we would find that deflection at midspan of a point load on a simply supported beam, PL cubed over 48 EI. So the stiffness would be 48 EI over L cubed. So kind of interesting, for the exact same beam, EI over some length L. The only thing that changes the stiffness is how it's supported. So a cantilever has more flexibility than the exact same element. In both models, but just different boundary conditions. And we end up with something that is about 16 times more stiff. So we'll do another one, and this would be for a fixed beam, so something that has a highly indeterminate beam. And so, though you wouldn't have to be able to solve for it, but it would turn out that the deflection at midspan would be PL cubed over 192 EI. So the stiffness in the translational direction would be 192 EI over L cubed. So you kind of get a relative feel for the stiffness. And that's the exact same beam, it's just we have more kinematic restraints, we have something more indeterminate. And those increased kinematic restraints create something that has more stiffness to it. So finishing up, we'll look at the rotational stiffness of a beam. And so if we wanted to model this beam as a rotational spring, we would need to track the moment divided by the rotation out at the end of the beam. And so looking in the deflection table, we would find that for a simple cantilever, we would have a rotation at the free end of ML over EI. That would give us a stiffness of EI over L. So we'll do it one more time here on a simply supported beam. We are going to track where the moment is applied. We need the rotation at that end. So we need the slope, partial V, partial X, here at 0 because the moment's applied at 0. And we would have M, the slope would be ML over 3 EI. So we'd have 3 EI over L as the rotational stiffness. You'll have this for a homework problem. This is an indeterminate beam, and you'll be asked to find the rotational stiffness out at the end of that beam. So we're going to need to find the slope out there at 0. And so that'll be a nice indeterminate problem review for you.